Hey, this is Horner, and these are the uniform circular motion and non-uniform circular motion problems. So first one here is 4.23, and this one basically just wants you to go through and figure out how many revolutions does the object make that has the angular velocity versus time graph that you see here. One of the things you need to review is go back and look at all of the angular or rotational motion equations, and so we'll make sure that we do that in class. But this is the first one, and it's basically just the angular velocity or the angular frequency is equal to the change in the angle divided by the change in time. So all I've done here is just reset them so that they are solving for how much angle there is. So if we look at the equation and use it as our guide, you'll notice that here is our angular velocity and our time. And if you find the area underneath, which would be the integral, we end up finding this times this. And if you take the angular velocity and multiply it times time, you'll notice that the seconds cross off and you're left with just radians, which is our just our displacement or our angle that we have. So for this first one, we're going to take 20 times 2, and we end up with 40 radians. For the second one, you actually have a different structure here. So you've got a trapezoid, and to find the area of the trapezoid, we're going to take the top plus the bottom and divide by 2, and then multiply that value by the height. So the top, you could say, is here. The bottom would be this part. Your height would be here, so you almost have to rotate this. And then you don't worry about this angle that you see here. So we're going to take A plus B, so we've got 20 plus 10. So really what I did is I said this is 20 here, this is my 10. We're going to divide that by 2 and then multiply times the height, which is 1, and you end up with 15 radians. Our very last one is just the square here, and so we're going to take 10 times 1. And because this one does stop at 3.7 seconds, and that's what they wanted to know, you can't use 1 here. Instead, we're going to take 3.7 and we're going to subtract 3 from that, and that will give us 7 radians. We're going to add all of those radians up together, and once you do that, you end up with 62 radians. But this one doesn't want radians, it actually wants revolutions. To go from radians to revolutions, we're going to use this conversion. There's 2 pi radians and 1 revolution, and we'll kind of talk about it here in a second again too. But we're going to take that 62 radians, multiply it times 1 revolution divided by 2 pi radians, and we get 9.9 revolutions. For the next one, this is 4.26. The Earth's radius is about 4,000 miles, so we've got that guy right here. And the next thing that has here is it is about 5,000 miles from Kampala, the capital of Uganda, and Singapore. They're all on the equator, and so we can just see that that 4,000 mile radius is going to be for both. This is an arc, and so it's got a length of 5,000 miles. There's our radius of 4,000, and here we know that the arc length is equal to S. The flight from Kampala to Singapore takes about 7.1 hours, and this is the plane's angular velocity. They want to know what is that relative to the Earth's surface, and they want to give us our angle and our answer in degrees per hour. So basically, the first thing we need to do here is find out what is that angle. So we're looking for this interior angle here. We know the arc length is 5,000. We know the radius is 4,000. And so you end up with 1.25 radians. Now I need to take that radian, so we need to convert it to degrees. If I have a circle, we know that a circle is 360 degrees. We also know that it's 2 pi radians. And if I take 1.25 times that 360 divided by 2 pi radians, I get 71.62 degrees. At this point, we've got omega, so remember that is the angular frequency or the angular speed. That's equal to the change in the angle over change in time Change in angle is 71.62 degrees, and our time here is 7.1 hours, so we get about 10 degrees for every hour. For our next problem, this one is 4.30. I've got a 3,400 meter high mountain. It's located on the equator. So here's the mountain. This is not drawn to scale. And the radius of the Earth is about 6,400 kilometers. So I've got both of these numbers in kilometers. The mountain would, if it goes around one time, would do like that. And so we could say that we want to find the circumference that it is making based on knowing that the Earth's surface is at 6,400. If we do that, we can find out how much faster this point is going than the point on the surface, because that's the difference between the two. And that's exactly what they want us to find. How much faster does a climber on top of the mountain move than a surfer at a nearby beach? So what I did is I said there's 2 pi times that 3.4, and that is not really a radius, but that is that difference between this entire thing and just the mountain height itself. And you get about 21.36 kilometers. So now that I know that, I've got 21,360 meters. That's just this guy right here in meters. And in 24 hours, which would be all the way around, we find out that we are moving. And so next thing I did is I went ahead and converted the hours to minutes and the minutes to seconds. And I did all my math and got 0.25 meters per second. And that is the difference. That's how much faster that climber goes. So the climber's not going 0.25 meters per second. That's just how much faster they're going. And that's why we did just the relative difference between the two. And those are the 3 problems for the very first section just on uniform circular motion.